Morning. I found another way to try and do a video. We're going to try this out. So I want to do a couple of videos explaining how to do IFF charts and like how to do them with a problem. So I'm doing a couple of example problems. Here's their first one. A ball of mass 3 kilograms is moving 2 meters per second to the right and strikes head on a ball of mass 1 kilogram that is moving 2 meters per second to the left. Balls stick together on impact. What is the magnitude and direction of the velocity of the combined mass after the collision? So remember that we want to set up an IFF chart first, an if chart. So this is going to be our, oh goodness gracious, this is going to drive me crazy. Let's erase this. Let's remember this is our initial. There we go. Situation. This is going to be our final situation. And this is a force time graph, which there's no information on force. There's no questions about impulse or anything like that. So we're actually not going to use this graph this time because we don't need to. Sometimes it comes in handy. Today it's not, so we're just not going to do it. Let's draw our initial situation. So first, I have a mass of 3 kilograms moving 2 meters per second to the right. So let's add some scale to my graph here. And I want it to be the same scale on both. And each of these ticks is 1 meter per second. So that means that if I have 3 kilogram mass going 2 meters per second, it's going to look something like this. Red. It's going to look like that on the bar. And if I have our 2 meters per second to the right, that 1 kilogram mass, it's only going to be this wide. And it's going to 2 meters per second. Yeah. Tell you what, all these straight lines really making me see how crooked my handwriting is. Not sure I appreciate that. Okay, so this is our initial situation. Remember, our initial and our final have to have the same momentum, so the areas of the two graphs have to be equal. I know that they're going to stick together, but I don't know their velocity. So I'm just going to leave a space here for their combined width. So it should be, that'd be 1 kilogram, 2 kilograms, 3 kilograms, 4 kilograms. So I know it's going to be this wide, and I'll save it for later. So let's, oops. This is going to be interesting. Okay. So can I just like, oh, I use 2 fingers? No. If I shrink everything, let's just shrink everything. There we go. Move it up here. Close enough. God, these videos are always so bad. Okay, close enough. Let's set up an equation so that we can actually do some math and solve this problem. So I know that my momentum initial has to equal my momentum final. In my initial scenario, I have 2 masses, so I'll say M1 and M2, and they're going 2 different velocities, so I'll call that V1 and V2. So this is going to be my momentum initial. This is all equal to PI. And then it has to equal my momentum final. It says up here that they're combined masses, they stick together. So I can go ahead and say M plus M, M1 plus M2, times my velocity final. Since they stick together, they should have the same velocity. Gosh, wouldn't it be weird if they had different velocities if they were stuck together? I don't think they'd be stuck together for long if they did that. Great, so now I can solve for what I want. So I want to know what V final is. So I'm going to get that by itself. So to do that, I just divide away M1 plus M2, and I'll do that for both sides. Okay, that cancels. So if I rewrite this, it's going to be V final is equal to M1 V1 plus M2 V2 divided by M1 plus M2. Let's plug in some values. So that's going to be, our value for mass 1 is 3 kilograms. our initial velocity for that mass is 2 meters per second, plus our mass of our other one, which is 1 kilogram. And then this is the important piece. Our velocity is negative, so make sure you keep up with your negatives. Momentum is a vector, not a scalar. Please use your negative. And then divide that by 3 plus 1, which is 4. So if I plug this into the calculator, I'm going to get velocity final is equal to 0.5 meters per second. Right? Yeah. 6 minus 4 divided by 4. Yeah. So now I can go back and I can draw out this is so good. My final area, my little area graph. And you can kind of visualize it, right? So if you take this piece and subtract it from this piece, it would be almost like, chopping off like this section of it, right? If you subtract this from this. So yeah, that looks pretty similar. I think that makes sense. Okay, well, this is just example one. I've got one more video to do for you guys. So I'll see you in the next video. This was a inelastic collision. The next one's going to be an elastic collision.